Hi everybody, this is Bob Cheesebro. I'm going to kick off the presentation and then I'll turn it over to Anoop about halfway through. So first we want to explore the motivation. So why do developers care about this technology, this explicit vectorization, explicit vector programming, this SIMD extensions to OpenMP? What's it all about? Well, to answer that question, let's look at a problem statement. So really the problem is that both core counts and the vector register widths per core have been increasing in later generations of hardware. And languages such as C, C++, Fortran are still inherently serial in nature. And so the language doesn't have the capability to express the parallelism that's inherent in the program where the hardware can take advantage of it. So the idea is that language extensions are needed to address this issue. So there's lots of different ways, there's lots of different methods that are available to developers to program using explicit vector programming. We're going to explore one approach, and that's the OpenMP4.0 SIMD approach. A couple of weeks ago, we talked about array notation, which is an Intel Silk Plus extension. Now we're talking about OpenMP 4.0. So our goal is to provide language extensions to simplify vector parallelism. This enables developers to extract more of that performance from their SIMD processors. So this graphic kind of depicts the trends and the growth of the vector registers and kind of depicts the evolution of hardware over time, starting at the bottom and moving to the top. So time is progressing from the bottom of the pyramid to the top. Into the page, we see core counts increasing. And as we go left to right, that dimension sort of expresses the vector width dimension that I'm going to be talking about. So over time, as time has gone forward, both core counts have been increasing and vector widths have been increasing. And way back, I'm not going to go into all the history, but just kind of a little gentle reminder, back in the days of MMX, this technology was invented to allow you to compute two integers at the same time on that single core that we had. And that was a pretty neat idea, so it was extended to include, when vector registers were increased to 128 bits with XMM, now we could compute 4 floating point values and 4 integers concurrently on that core. And then sometime in there we had multiple cores available. A little bit later we extended the size of the vector registers to 256 bits. That was during the Sandy Bridge, Ivy Bridge. We're still kind of in those days in a way. On those platforms, you can compute 8 floating point operations at the same time. Now remember, this is per core. Now with the advent of the mini integrated core architecture, those vector widths have increased again to 512 bits, which means that on a single core, you can compute 16 floating point values at the same time. That's per core. So with Mike, you may have up to something like 60 cores times those 16 floats. So you can see that this multiplicative effect of this parallelism is really giving us lots of computational power. But if you see that little dashed line representing auto-vectorization, that represents sort of that portion of the programs that the compiler, because it's constrained by serial languages, is able to address automatically. So what we need is these explicit vector extensions that let us span more applications and expose more of that parallelism. So let me give you a little graphical example of how this comes into play. So think of I've got 8 instructions that I want to compute in a loop on the left, and this is an old scalar loop, so it's using registers, but it only takes one value at a time. In those registers, it does some computation and goes on. Think of this as like a single lane highway where we're forcing cars to go down the lanes one at a time. Now I have 8 instructions that I want to accomplish, and it goes through the loop, and then it has to wait for the next instruction. And so you can kind of get this sense, this feel in time of how long it would take to process 8 array elements, one at a time through a loop. So that's the idea of a scalar loop. Now what we would like to do is say, well look, I have 8 vector lanes on this, let's say, Sandy Bridge architecture. If I've got floating point operations, I can compute 8 floating point operations at a time. So now I could process all 8 iterations of a loop simultaneously because I'm using all that vector width to my advantage. And so the takeaway here is to use all the vector lanes if possible. Now, that sounds great in theory, but what happens if you have real-world scenarios like a function call, a user-defined function call in the middle of your loop? And let's go back a little bit further in time. This is just kind of for simplicity so that the graphic didn't take up so much space here. So I'm going back to the SSE2 days where we had 4 vector lanes for the single precision floating points. So here, I wanted to vectorize all the vector lanes and let all 4 cars, 4 iterations at a time, go through my loop. But unfortunately, there's a single function call that would not allow me to let all 4 cars pass. That function call is a bottleneck. It's like a reduction down to a single lane of highway. And so that was represented just by a function call, a normal user-defined function call foo, let's say. So one of the things that we'd like to do is to remove such bottlenecks. And one of the things we're going to explore today is a declaration that you can use in OpenMP 4.0 to declare a user-defined function as a vector function so that now we can get rid of that serial bottleneck and we can use all 4 lanes or all 8 lanes or whatever the vector width is. So the idea is that we want to use SIMD-enabled functions to remove these kinds of barriers. So here's just a graphic depicting sort of the potential performance speedups. Now in this case, I'm talking about a double precision floating point operation. Okay, so if I'm dealing with double precision, those are 64 bits wide. So a 128-bit vector register back in the SSE2 days could therefore accommodate 2 vector lanes. You could do 2 things at once. In Sandy Bridge, Ivy Bridge time frame, 256 bits divided by the 64-bit width of the instruction of the data type, that would give me 4 vector lanes potential. And so that gives me a potential 4x speed up on my code. With Mike, with 512 bits divided by the 64-bit data type, that would give me potentially 8 vector lanes, and so a potential 8x speed up for Mike. So note that the wider vector registers allow for higher potential performance gains. Gains of 4x, 8x, even 16x are possible depending on the data type you choose and depending on the platform you choose, using this SIMD extension capability. So I want to just lay out just a few of the SIMD concepts before we get into the implementation details. This is sort of a conceptual framework that you need before proceeding. So first of all, many of you may be familiar with the compiler's ability to auto-vectorize loops, and that's great technology. And I mentioned it earlier that the compiler is unfortunately limited by the serial semantics of the language that it encodes for. So the auto-vectorizer, while it does a great job and it looks for loops that can potentially be parallelized, there's lots of things that the compiler can't recognize because the language makes it serial. And so there's some limitations there. But the nice thing about the auto-vectorizer is that to the developer it looks like a freebie. Just a compiler switch, no changes in code, and off you go. You get some performance. The problem is we're leaving some performance on the table because it can't tackle all cases. Now on the bottom, we look at assembler code, or some of you may be familiar with the SIMD intrinsics or the vector intrinsics. Now those things are great. They give you lots of power and flexibility. You can vectorize just about anything you can imagine with this technology. And you're responsible for doing your own bit twizzling and shuffling of registers and all that kind of stuff. So it's very powerful, but unfortunately it's not portable. So once you do this kind of optimization, say on a Xeon, then that optimization doesn't work for Xeon Phi, for example, or vice versa. So somewhere in between is what we're talking about today, and that's explicit vector programming. So explicit vector programming is more of a pragma-based approach that gives you both a lot of power and a lot of portability. So it lets you target more easily multiple platforms with one fell swoop, basically. So that's what we're going to look at. Now, I do want to call your attention to the idea that explicit vector programming puts a lot of responsibility on the developer, just as OpenMP threaded programming puts a lot of responsibility on the developer. With OpenMP threaded programming, when you write an OpenMP parallel 4 around a loop, You're taking charge and you're telling the compiler, look, compiler, I know that this loop can be parallelized, and I'll draw the foul if it gives me incorrect results. Similarly, with SIMD programming, it's the same idea. You're telling the compiler that you know that that thing can be parallelized using SIMD. And so there's a really strong correlation between the work-sharing constructs in threaded versions of OpenMP versus the SIMD ones. And in fact, a lot of the same constructs, reduction clauses, private clauses, and so forth. So if you're familiar with OpenMP work-sharing constructs such as the Parallel 4, then you should take to SIMD programming no problem. Now we're going to look at 3 technologies, actually 2 in this talk. There's sort of 3 components to explicit vector programming. One is array notation. Now we talked about that. That's a Intel Silk Plus feature. We talked about that 2 weeks ago. Today we're going to be focusing on SIMD-enabled functions and the SIMD pragmas. And these are particularly useful when auto-vectorization is limited because of that inherent serial nature of the language. And we need to explore other ways to conquer more algorithms and more loops to parallelize them. So here's just a snapshot. So we're going to be getting more into the details, but what we're doing here is we're attempting to SIMD-ize, vectorize some serial code up there on the left. It's just a simple loop that takes two arrays, B and C, it sums them and puts the result in an array A. So simple concept. So how would we do that? So here's the first sneak peek of implementation of SIMD. So down in the lower left, the way that you could get this to vectorize explicitly is that you could decorate that for loop with a pound pragma OMP SIMD. And that would tell the compiler, oh, that has implications. That means the n is not changing in the loop iteration. That means that the arrays A, B, and C are linearly independent, that there's no ambiguous pointers, that they're disambiguated, okay, that they're not conflicting in memory addresses. So that's what you're articulating when you see pound pragma OMP SIMD. So that's one way to decorate a loop, if you will, to get SIMD parallelism out of it. Another way is to use array notation. Now, I know this talk is about OpenMP 4.0, but I do want to mention array notation because it can be used orthogonally. It can be used in a complementary fashion with some of the features of OpenMP 4.0. So that's an Intel Silk Plus system. We talked about it 2 weeks ago, and notice that there is no loop. The parallelism is built into the syntax. Now, let's take a look at the SIMD-enabled function with the Intel Silk Plus array notation format. What we're doing here in the upper portion of that code in the lower right is that we're decorating that function declaration. We're saying that that function foo will take vector arguments as inputs, and it will return a vector argument on the return type. We do that just simply by saying pound pragma OMP declare SIMD. Now we've turned that function from a scalar function into a vector function. Turns out we still have a version. The compiler is smart enough to give us a scalar version of that function too if we ever need it in another portion of the code, but it will also give us a vector version of that function. Now, if I wanted to implement that function and get all those SIMD lanes operating, then what I could do is, let's say, use array notation in this example. I could say, look, I'm going to pass the vector B and the vector C to the function foo, and foo will return to me an array, a vector A. And so this would be a very simple way to implement that newly declared vector function foo. Now I'm going to move forward here and turn it over to Anoop, who's going to tell us a little bit more on the details on SIMD-enabled functions and the pound pragma SIMD. Anoop?
Thanks, Bob, for that introduction to vectorization and also mentioning explicitly the significance of the vectorization in today's architecture. So I'm going to take this forward by explaining or deep diving into a couple of explicit vectorization tools which is available as a part of OpenMP 4.2. The first one being the SIMD-enabled functions. So let me get started with that. Firstly, what is SIMD-enabled functions? So if you see traditionally, when you use either C or C++ programming language, for instance, you can abstract certain functionality by encapsulating that functionality inside a function. Now, that function traditionally can accept scalar arguments. It does some scalar processing and then returns a scalar result back. Now that's a traditional case. Like what Bob showed before, what if the same function, the traditional function, is being invoked inside a for loop, which you are apparently targeting for vectorization? Can you imagine what will happen? Well, absolutely, because that 4-lane road which you saw in Bob's graphics would turn to a 1-lane road. And that's because the function can accept and process only scalar arguments. How do you work around that? Because obviously, not all loops are simple in the real-world application. There are so many applications out there where you invoke functions within the loop and you expect that loop to get vectorized. The potential bottleneck is the function call. But what if there is a means for us to vectorize that function so that the function, rather than operating on scalar arguments, this time can operate on vector arguments? Think about it, guys. That's exactly what SIMD-enabled function does. So, and this miracle can be done by just using a pragma OMP SIMD declaration. In this case, you can say pragma OMP declare SIMD, and that pragma actually hints the compiler that, you know what, go ahead and generate a vector variant of this function too, apart from the traditional scalar variant. And where do you specify this pragma? Well, every function prototype has been registered in a header file. That's the right place where you go and annotate a particular function as a SIMD-enabled function. The reason why you do that is because every time you annotate at the header file where the function prototype is defined, that definition is visible across multiple call sites. And I'll get to the call sites soon. So in short, SIMD-enabled function lets you create vector variants of the function, whether it be library functions or it be a user-defined function. Well, this capability is available as a part of Intel Silk Plus, of course, the technology which we talked about 2 weeks back in another webinar, and the OpenMP4 specification, which we are talking today. Just to give you how it looks in the code perspective, here it is. In the first blue box, you have this function foo. Let's assume that the pragma OMP declare SIMD is not there right now. So if you neglect that line, it's a simple function which accepts some float arguments. Again, they are float scalar arguments, and does the processing and then returns a float value as a result. Now, traditionally, the way you call this function foo is by using a scalar call, which is actually mentioned in the blue box, the second blue box there, where e is equal to foo of, and then you pass the 4 float arguments. You could see that e as well as the arguments a, b, c, d are scalars and floats. Now imagine if the same function called foo is happening inside a for loop, which is running from 0 through n. Now in this case, let's again assume that the pragma OMP SIMD is not there as of now. In that case, for every loop iteration, you are invoking the scalar version of the function foo. Now let's imagine, for instance, that we are putting this pragma OMP SIMD, which means you're forcing the loop to be vectorized. Now, if the loop is forced to vectorize, we obviously expect a vector variant of the function foo to be available so that the loop can be vectorized. That's quite logical, because every time you vectorize it, you take vector operands and you expect the function to handle the vector operands. Now, how do you enable the function foo to handle those vector arguments? That's by putting the pragma OMP declare SIMD for the function foo right at the top here. So the way you do that is, once you specify this pragma OMP declare SIMD, the compiler is going to generate a vector variant of this function too. And this time, when I invoke this for loop and call this function foo, it's not going to call the scalar variant, but it's going to call the corresponding vector variant of the function foo. Now there's another way to invoke the function foo using the vector operands, and that's by using Intel Silk Plus array notations. Well, as you all know, array notations, it's a notation for the array by which you can specify or explicitly specify the vector which you want to operate on. So as simple as that, it's like a vector operand which you specify rather than the traditional scalar operands. So here you could see that when I invoke the function foo, I'm going to pass vectors rather than traditional scalars. And as long as I have declared it as SIMD enabled, this function call will actually work fine. So that's the advantage of using SIMD enabled functions in your code. Well, the concept, like I said, every time you declare a function as pragma OMP declare SIMD, the compiler which is compiling the code, like for instance Intel C++ compiler which supports OpenMP4.0, so that's going to generate a traditional scalar version, which means your legacy code will work fine, but it can also generate vector variants of the function. Well, now the obvious question would be, well, do you mean vector variant? Is it just one vector variant, or are there multiple vector variants? For folks who are thinking in that angle, well, obviously you're right. You can generate multiple vector variants of the function. How do you do that? I'm getting there. Now, the important point here is the scalar and the vector variant. So what I mean is, as long as you've enabled this code, the code is portable on previous architectures too, because you don't neglect the scalar part of it. Again, the caveat. The caveat is that which functions would you target to be SIMD-enabled functions? Well, the obvious answer is you want to actually do a hotspot analysis of your application, pick those prime hotspots or prime functions which is contributing or which is a busy function in your application, and see how SIMD-enabled functions can be applied on top of it. Why I don't recommend all the functions in your program to be SIMD-enabled is because imagine every function has multiple different versions available. You're loading up your binary. So the way you should use it is to analyze the hotspot and make sure you apply the SIMD-enabled function on the right hotspot to see the performance improvement. Well, like I said, when you specify multiple variants of the multiple vector variants, obviously, just by specifying pragma OMP declare SIMD, you can't generate multiple variants. You need something else to it, and that's where the clauses come in handy. There are different or multiple clauses which we offer as a part of the OMP declare SIMD pragma. This slide will be explaining a couple of them. The first one is a uniform clause, the other one is a linear clause. Just to give you a background, let's focus on the yellow box out there. So you could see that you have a function foo which accepts a float pointer and an integer I. So if I want to enable this as SIMD-enabled function, all I specify is pragma OMP declare SIMD at the function prototype. And what the compiler does is it will translate. When I say translate, it's a direct translation of this function scalar equivalent to a vector equivalent, which means it's going to translate my first argument, which is a float pointer, to an array of float pointers, and the second argument, which is an integer, to an array of integers. We'll just sit back and look at that. Is that the way you want the compiler to do it? Does it make sense to pass a float? Does it make sense to actually pass an array of float pointers in this scenario? Is that the intended behavior? Well, of course not. The reason is because all you expect to do inside the function is, well, the float pointer A has to be shared across all the iterations, and the only thing which is changing is the index I. Now again, if you keenly observe, if this is invoked within a for loop, for instance, where the loop index is increasing by 1, then the I index, which is the second parameter here in the foo, that is having a trend. The trend is I is incrementing by 1 in every iteration, which means it's linearly increasing by a unit stride. Now what if I can specify these two behavior or the behavior of these two variables explicitly when I request for a SIMD-enabled function from the compiler? Well, that's exactly what the clauses help me do. If you see the blue box at the top, I've specified A to be uniform. What it specifies is, well, when you specify something as uniform, that value is shared across all the iterations. And the I variable is specified as linear, which means it is incrementing linearly, and it's incrementing by a value of 1, which is unit stride. That's what is specified by linear, and then within the braces, it's like I:1. So this is what the SIMD-enabled function clauses enable you to do. Basically, your articulation of what is happening within the function or within the loop is much more clearly explained to the compiler by using these clauses. Regarding the SIMD-enabled functions invocation, like I said, just because you're enabling a function as SIMD-enabled, that doesn't mean that your legacy call it won't work anymore. Like in this case, let's assume that there is a function my_SIMDF Now that's expecting a float argument, and it's going to return a float value. Now, when I specify the pragma OMP declare SIMD here, that actually means that I'm enabling this function as SIMD enable. Now let's see the invocation part. So you can see that the first row in this table is actually the traditional scalar invocation, where you have a function being called within a loop, but I'm not forcing the loop to vectorize here. So this is the traditional scalar invocation. But the second row says that, well, it's the very same loop, but this time I'm forcing the loop to be vectorized by pragma OMP SIMD declaration. So here it's going to call the vector variant of my SIMD my underscore SIMDF function. And finally, the same vector variant of this function can be invoked using the surplus array notations, where you actually invoke the function explicitly by specifying a vector arguments, and also you receive the vector results back. So this is how you invoke a function which is SIMD enabled. So all the three variants are supported. Well, I did promise you guys that I would talk about the call side dependence and why the function prototype in the header files should have the SIMD enable function declaration too. Well, the reason it will be explained here clearly. First, let me look at the callee side. The callee side is the place where the function has actually been defined, for instance. So here the function foo, it's pretty simple function which accepts an integer pointer a and an integer I. All it does is just print the output to the standard output stream. Now, in the case of the callee side, you see that I specified pragma OMP declare SIMD, which means I expect a SIMD enable function or a vector variant of this function to be generated. But that's not it. I have specified the clauses too. I have imposed the condition on the first argument, which says uniform of A, imposed the condition on the second argument, which is linear. I is going to be a linear variable with a stride of 1 for every iteration, and the SIMD length. The SIMD length clause is used for specifying the vector length or the length of the vector operand which the function is going to execute. Now that's about the callee side. Let's go to the call side, which is the second box. So you can see that it's a for loop which is running from 0 through n, and there is an invocation of foo within the for loop. And you can also see there's a pragma OMP SIMD and safelength 4. The safelength 4 specifies that, again, consider the vector length of 4, means 4 integers packed into the register. So here you expect the vector variant of the function foo to be called. Is that happening? Well, you compile the code and you generate the vectorization report, and you could see that the OMP SIMD loop was vectorized. And another important message is the function was vectorized. See what I mean? You were able to successfully vectorize this loop, and in that process you could do that because the function was vectorized. So your function was vectorized, because of which the loop was also vectorized. That's what I mean by the actual power of SIMD enable function. Had the function not vectorized, the loop wouldn't have been vectorized. That's the drawback. For more information on this, please feel free to go and access the URL down here. It will have more information on Intel Developer Zone. Well, that's a good case where you have a particular vector variant of the function. You call the vector variant, and of course the vectorization is happening fine. Now, if you see the difference between that slide and this slide, the only difference is in the call side. You can see that instead of one call side, there are two call sides. The first for loop is same as what we saw on the previous slide. The second for loop is something interesting. If you see the second loop keenly, the loop is running from 0 through n, and again there is a function foo being called here. Well, the first argument is the same, which is a, but the second argument is k. Now the argument k is not the same as the argument I, which was passed in the first invocation, because argument I was incrementing unit strided fashion, but here k has no regular pattern. The k value is brought from b of I. So it purely depends on what b array is storing. The k value is dependent on that. So there is no specific pattern. Now, if I invoke this function here, would it call the scalar version or would it call the vector version? That's the question. So the best way to do that is to compile that code and run it using Intel C++ compiler, and then run it. And you would see the vectorization report first. the vectorization report during the compilation phase clearly says that no suitable vector variant of the function foo was found. What does it mean? It means that, well, I do see a vector variant of the function foo available there, but that doesn't suit the invocation site which you're using right now, because your second argument k doesn't match the criteria of the vector variant, which is, oh wait a second, the second argument which you pass need to have the linear unit stride behavior, which I don't see here. So the compiler is actually smart enough to identify at the call site level whether it is asked for a scalar call or for a vector call, depending upon the available vector variants. That is why I specified before that you got to make sure the function prototype has the SIMD enabled declaration specified, because you include that header in all the call sites, and that visibility is given, that visibility of what vector variants are available is available to the compiler, and it can make a decision as to call the vector variant or stick with the scalar variant. In this case, it's going to call the scalar variant of the function rather than the vector variant. So that shows the compiler is smart enough to identify it. Well, now the compiler is smart, so how do you show your smartness in vectorizing this loop? Well, that's how, by specifying another SIMD-enabled declaration. So this is what I meant by you can have multiple SIMD-enabled functions or multiple vector variants of the same function. So the only reason the previous loop wasn't vectorized is because the original vector variant had an extra restriction on the second argument. Well, what if we can knock that out? That's what I do in the second case, where I specify pragma-OMP declare SIMD uniform A, SIMD length 4. You see that the linear criteria which I imposed on the second argument is knocked off. Now I have two vector variants of the function, and this time you can see that the OpenMP SIMD loop was vectorized. So this is the power of SIMD enabled function. I hope I set the motivation right for you guys to go ahead and try this on your application. So that's it for the SIMD enabled function, guys. Let me quickly move on to the SIMD loops, which is another explicit vectorization tool which we offer as a part of OpenMP4 spec. So again, the motivation. So here we have a simple function, add_FL. Now this function is apparently accepting a bunch of float pointers and an integer. And if you see what is happening inside the function, let's assume that the pragma-OMP SIMD is not available right now. So you have a simple for loop which is running from 0 through n, and all it does is add the elements of the array and then store it into the A array. Now when you actually compile this program without the pragma-OMP SIMD, the compiler is going to take a defensive stand. Well, that makes you all curious. Why would the compiler take a defensive stand? Well, the idea is very simple. When you compile your code with any compiler for that matter, you don't want the compiler to do an aggressive optimization and then finally lead up in wrong results. So here, the potential assumption which the compiler can make is that, okay, I understand that there are these many pointers which is pointing to the memory. Now, the only thing which I don't have clarity about is, are these mutually exclusive memory locations, or do they have a memory aliasing happening here? Well, that's not clear from this code actually, and that gets me back to the point which Bob mentioned, which is the limitation of the C++ language semantics. Unfortunately, the language wasn't designed for expressing these kind of details, and once the developer doesn't have the capability of expressing these kind of details, the compiler doesn't have enough information to make that extra level of optimization. By pragma SIMD or pragma-OMP SIMD and pragma-OMP declare SIMD, what we offer is an extension to the existing language. And by doing that, we give that expressiveness for the developer. He can better articulate on what's happening under the hood or in his algorithm so that the compiler understands it and it can do the necessary optimization. So here, by mentioning the pragma-OMP SIMD, we explicitly say as a developer that, you know what, go ahead and vectorize this loop. I'm sure there is no memory aliasing happening here. That's what this tool is capable of doing. Another example here, you have a simple loop which is specified in the blue box there. The potential things which the compiler can assume looking at this loop is that, well, I have A, B, and C arrays here. Are they aliased? Is there some memory alias happening? Secondly, is there a way to specify explicitly that there is a reduction happening on the variable sum out there, so that when it vectorizes, it does take into account that. Third thing is, since there's a reduction happening there, will there be any problem in, or will there be an accuracy problem if I change the order of computation? Well, that depends on application to application. Some applications can handle that. Some applications, they are very picky about their accuracy. So the compiler takes a defensive stand here, and it would leave it to the developer to explicitly specify certain parameters. So the compiler is dependent on the developer to specify certain things so that it can go and do the extra level of optimization. How do you do that? Here it is. So in this case, you specify that by using the pragma OMP SIMD, which means you are basically forcing the compiler, saying that, you know what, there's no memory aliasing happening, go ahead and do it. And while you do that, please do consider that the sum variable is a reduction variable, and the reduction operation is the plus operation. This is what the explicit vectorization tools are capable of doing. They give us that extra piece of a tool or a weapon by which we can specify what is happening in your algorithm, so that the compiler can understand, oh, this is what is happening, so this is how I can optimize it for you. If you don't specify, which is what happens in the scalar coding or traditional C++ coding, then the compiler has to take a defensive stand, because you don't want optimization at the cost of accuracy. Here's another loop. Interesting thing about this loop is that for the first time, if anybody looks at this loop, he would say that, oh, you know what, there are two reduction operations happening, one on sum, another one on p, and the operator is the plus operator. But if you keenly observe this loop, there are no two reductions. There is just one reduction. The sum variable is a reduction variable, the sum plus equal to asterisk p. But if you observe what is happening for p plus equal to step. Now, the p pointer is every time, for every iteration, it's incremented by a value step. And if you look up, the step is basically a constant 4. Actually, what's happening with every iteration is, well, there's a reduction happening on the sum variable, but in the case of p, you are incrementing linearly by a stride of 4. So obviously, if you want to use pragma OMP SIMD, the right clauses which would explain the behavior to the compiler is by using the reduction clause with an operator's plus on the variable sum, and a linear clause on the variable p with a stride of step. And that's what I specify. And when I specify this, the compiler has enough information about what's happening inside the loop, and now it can go ahead and generate the right code for the targeted architecture, ensuring that the performance is guaranteed. So this is what OpenMP 4.0 Pragma SIMD is enabling us. It gives that extra bit of power which the traditional programming languages lack. Like I said, the Pragma notations, this is a power which is given to the developer. So you got to make sure that, like, this is not to be targeted for those loops where you feel that the vectorization can actually cause wrong results. For example, if you have some data dependence in your loop, like if your previous iteration value is what is used in the current iteration, you don't want to vectorize those kind of operations, because when you explicitly vectorize those by using Pragma SIMD, you are going to potentially result in, wrong values. So you got to make sure you as a developer, when you use Pragma SIMD or Pragma OMP SIMD, make sure that the loop is a perfect candidate for vectorization. Well, like I said, in software engineering, we always say that the code speaks louder than words. So I chose to have a simple code snippet which kind of demonstrates most of the clauses which comes with Pragma OMP SIMD, rather than have a couple of slides that explains about what it does. So here it is. So you have a simple nested, perfectly nested for loop here. And if you see what's happening inside the for loop, it's the same code which you guys saw in the previous case. So let's see what these clauses are doing. I have used a bunch of clauses here. So let's start with the first one, which is collapse 2. So when I use Pragma OMP SIMD, I say that go ahead and vectorize this loop. And when I say collapse 2, what it means is, well, I see a 2 nested for loop here. When you do the vectorization, could you please collapse the two loops into one and then start the vectorization. So traditionally, vectorization is targeted for inner loops, but in the case of Pragma OMP SIMD, that's not the case. You can also target the outer loops, or you can do this operation, which is collapse perfectly nested loops and then apply the vectorization on top of it. And the tool specifies that I want to collapse these two loops. Now, obviously, there's a reduction operation happening on the sum variable, and the reduction operation is addition operation. And again, the linear clause, which is specified for the variable p, and the linear stride is basically step. Now, what does the align specify? The align, if you see the pointer, the p variable, it's a reference variable. It's a pointer, which is pointing to a memory location. Now, as long as I can specify that aligned, the p is aligned by 16 bytes, for instance, which is what is specified here, the compiler can decide to use aligned moves rather than unaligned moves in this case. So that makes it so you can give that extra bit of information to the compiler on which instructions it can choose. And finally, the vector length. Say, for instance, in this case, I'm targeting for SSE, and considering that I'm operating on floats, I can pack 4 floating point values into the XMM register, which has a capacity of 128 bits. So that's why I specify the safe len as 4, which means use a vector which has 4 floating point values. So this, in simple, demonstrates how to use the clauses and explicitly specify what's happening inside the loop. And it also gives you a control as to, okay, what should I be doing, or what the compiler should be doing on which instructions it should choose, is it an aligned or an unaligned axis. I hope I've set the motivation right here, guys, for both SIMD-enabled function and Pragma SIMD or Pragma OMP SIMD. These are the 2 explicit vectorization tools which OpenMP4 offers. Just in case you guys are really curious enough to try this right now on your application, well, the obvious question is, how do I get this? Which compiler actually implements this spec, and how do I get that compiler? Well, the answer is in this slide here. OpenMP4 SIMD extensions is supported by Intel C++ compiler, and you can get the compiler either from Intel Cluster Studio XE, Intel Power Studio XE, or Intel Composer XE suites. Well, please feel free to go and click the URL which is there in the blue box, and that will take you to the site where you can download these products and try it for yourself on your applications. Always remember to go and check on openmp.org, because that has the spec sheet as well as very good code samples which demonstrates as to how to use these explicit vectorization tools. Here are some references. These references will really come in handy for you as you ramp up an OpenMP 4.0 explicit vectorization tools. One thing which I really specifically want to call out is the performance essentials with OpenMP 4.0 vectorization. That's a video series which is put together by Bob Cheesebro, and that clearly explains individual vectorization tools in great detail. And we have also put together BKM, a best known methods documentation on how to use explicit vectorization, or how to start about targeting your code for vectorization to start with. So this has a very good reference. Please feel free to go ahead and refer that. And I think that's it for the presentation, guys. So if you have any questions, this is the right time to shoot that. Off to you, Mike.
Great, thank you. Yes, we do have some time for some questions. So we've had several that come in, and that's great. And if you have any more, please put them in the text field and send them in. There was a question about downloading the presentation. This has been recorded, and as soon as we have the archive up, it will be there with a PDF file of the slides, and I'll be sending out an email to everyone once that's available to you can view this again at a different time. So a couple of questions. Do you have a book for programming with explicit SIMD and Intel compiler?
Could you repeat that, Mike? Do we have a book?
Is there a book for programming available for the explicitly for SIMD and Intel compiler?
I'm not aware of of a book that just covers that. There's an excellent book by James Reinders and Jim Jeffers that covers mainly Xeon Phi programming, but they have some excellent chapters in that book on some of this technology.
I believe you can find that on, I think, on Amazon or any of the online book stores that are available. You just search, I think, either for Xeon Phi programming or, like Bob said, under James Reinders, and you should be able to find that pretty easily. Okay, next question. So do you have an example where you want to parallelize the loop and also use Pragma OMP SIMD on the loop?
Yes.
That's a really good question, Anoop. Yeah, go ahead. Yep.
Okay. So right now I'm in the reference slide here. So the last bullet, which is enabling SIMD in program using OpenMP4.0, please go to that URL, and that will take you to an article which is published on Intel Developer Zone, and that explains on how to apply both threading as well as vectorization on a same for loop. So that's possible. Yes.
And yeah, and that also kind of brings up some of the advantages of each of the different technologies, SILK Plus and OpenMP4.0. Yeah, it'd be better to refer to the article there. But for example, with OpenMP4.0, you can do both the threaded and the SIMD parallelism on the same loop. SILK Plus, there's more of a limitation there, but with SILK Plus, you can do array notation. So there's pros and cons and trade-offs, but with OpenMP, you can do both.
Okay, great. Question asks, how does this compare to Intel SILK Plus constructs?
So the Intel SILK Plus constructs are very similar. In fact, the underlying technology is basically the same. Intel kind of developed this with the Intel SILK Plus in mind, and then they went and influenced the OpenMP.org committee with the value of this, really. So really the underlying technology is the same. It's a different syntax. So in another webinar that I think we did last year, we talked about the Pragma SIMD in SILK Plus. That's basically a euphemism, or it's an analog for the pound Pragma OMP SIMD that we have here. And then there's some directives in SILK Plus that let you get at the SIMD-enabled function technology. It's a different syntax that I won't go into here for SILK Plus, but it is basically exactly the same conceptually as the pound Pragma OMP declare SIMD here in OpenMP 4.0 spec. So it's the same stuff, same caveat, same advantages, just different decoration with the syntax.
That's right. Just to add to what Bob said, like if you see, it's a Pragma-based approach for OpenMP 4.0, and having a Pragma-based approach for both SIMD-enabled function as well as for Pragma OMP SIMD is that if you actually use a compiler which is not supporting OpenMP 4.0, in that case these Pragmas will be ignored. There won't be any error thrown. So folks who are interested in porting their application or trying it on different compilers, well, that's one added advantage. But SILK Plus, you will have to, the Pragma SIMD is perfectly fine if you're just targeting for vectorization. But if you're using SIMD-enabled functions there, you use a decal spec or an attribute tag, and like that can throw an error if the compiler which you're using doesn't support that. So you'll have to write it for specific to Intel compiler there. So like I said,
so the beauty of this talk is stay with OpenMP 4.0 and you get the Pragma-based umbrella of protection all over. And if you want to be a little more surgical or whatever, maybe not more surgical, but you have at least an alternative approach with SILK Plus. But OpenMP lets you do the Pragma thing, cool. So.
Okay, there was a question, and then I see that Ron answered it online, but I'll let you also answer it again. It talks about which version of Intel compiler supports OpenMP 4.0.
Okay, So like Ron mentioned, like the Intel C++ compiler 14, in fact Intel compiler, both Intel C++ and as well as the Fortran compiler, 14.0 supports OpenMP 4.0 SIMD extensions. As far as the offload extensions are concerned, like which is also part of the OpenMP 4.0 spec, that's fully implemented in the 15.0 compiler, which is in the beta program right now.
Okay. It does Intel Cluster Studio XE update 4 support OpenMP 4.0?
I didn't capture that. Could you please come again?
Which version of Cluster Studio supports it?
Well, it's actually,
go back to
Cluster. It does say, does Studio XE update 4 support OpenMP 4.0?
Studio XE. Which Studio XE? Is it Palo Studio XE?
I'm assuming so.
Okay. So as far as I understand, the Intel Palo Studio XE does support a 2013 SP1 for Composer XE. Surely supports it because that comes with Intel C++ compiler or Fortran compiler 14.0. So as long as you're using the Composer XE suite 2013 SP1, you're fine.
Okay. Next question asks, is Pragma OMP SIMD a work sharing construct?
I'd say it's conceptually similar to work sharing construct. I went and looked at the spec not too long ago to see that same question, and they didn't list it explicitly as a work sharing construct. They had work sharing constructs listed as like single and sections, but then right next to that description in the spec they called it SIMD extensions. So I would say that technically it's probably not considered that if you're an OpenMP purist, but conceptually it essentially is. It's so similar to the same kind of an idea with OpenMP Parallel 4, which I would consider a work sharing construct, that conceptually it's basically the same idea as a work sharing construct. It just doesn't divvy up the threads to do it. We're talking about vector lanes, and so this is done. The SIMD parallelism is applicable per thread, per core, basically. So I think maybe that's why they don't really consider it a work sharing construct technically, because you're not divvying the work among the threads. Each thread can do this, get this parallelism within itself. So maybe that's the technical distinction. I don't know.
This question asks, which CPU architecture supports OpenMP4?
So see, when you say OpenMP4 or those SIMD extensions, any processor which has SIMD registers, obviously they can, we can use OpenMP4 technology to target those CPUs. So anything which starts with SSC2, for instance, or SSC, and like you can start targeting using OpenMP4 specification. So which means
so
like
the core platforms, the Xeon platforms, Xeon Phi, like Anoop said, anything that supports SSE, SSE2, AVX, AVX2, any of the variants, SSE3 and 4 and all those, if it supports that, then this applies.
Yeah, that was the next question that came in, if OpenMP 4.0 supported Intel Xeon Phi.
Yep, absolutely. Both in the native and the offload mode. So it's yeah.
Okay. And another question, and this is our final question, unless we get a few more that come in. We still have a few more minutes. Ask, can we target the same for loop using OMP parallel and OMP SIMD pragmas?
Yes, you can do that. Again, like how do you do that? I have explained it in the enabling SIMD in program using OpenMP 4.0 article, which is the last bullet in the reference slide here. So that article clearly explains as to how to target that.
Great. All right, well, I think that's all the questions that we have, and we're 5 minutes to the hour, but thank you everyone for joining us, and appreciate Anoop and Bob with the presentation. Thanks to everyone for joining us. We have more webinars coming up at this time for the next several weeks. We hope to see you again and have you join us for another webinar. Thank you, everyone.
Yep, and just another quick note, Mike, unless it's already shut off.
Sure.
I did want to make note. We did refer just briefly in those last slides that this same technology is applicable to Fortran. So even though our examples here were in C and C++, both the SIMD pragma and the SIMD enabled functions are applicable to Fortran as well. So please take a look at that. You can go to the openmp.org spec and see those cheat sheets and how you do that. But if you know any Fortran developers, I know this was targeted to a C and C++ crowd, but if you've got buddies that are doing Fortran, you can point them to that as well.